Okay. So welcome back. Hope you had a relaxing weekend. I know that this is kind of the middle of the quarter, so people are kind of like busy uh, with all the midterms and all that. So hope things are going well. This is the beginning of the kind of like the second chapter of this course, which we're going to talk about out of order execution and superscalar. So lots of exciting stuff. These are like more modern stuff. So kind of like the first chapter was more on focus on the fundamentals, but this is kind of more on the advanced topics, more advanced topics that is being used more regularly in almost all the devices that you're using these days, including all of your cell phones and so on and so forth. Solution and rubric. So for quiz one, hope you guys had a good quiz. How many of you think you did well in the quiz? Or maybe, okay, so let's ask it differently. How many of you guys think you didn't do well in the quiz? Few of you. All right. We're gonna post the rubric. Yeah, answer this question as well. This will give you a bonus points for it. I didn't put it in the quiz because to save some space. I don't want to kind of like waste an extra page for that. We're gonna you can do it for I mean it's going to be there, so you can do it within a week or so. You guys get the first hand, but just scan this code whenever you're watching this video and you get the points. Rubric will be posted. The rubric will tell you exactly like, you know, where, like how we're going to distribute the points. We usually distribute the points so that even if you kind of miss one part of the answer, you don't like penalize all the way through. And yeah, so you will see the rubrics sometime soon as well. The grading timeline is going to be, we're pushing to kind of finish this as soon as possible, but you know, it's not an easy task, unfortunately. It's like a 300 something papers that needs to be like thoroughly graded. So it's not going to be next week for sure, but hopefully before quiz 2 or sometimes around that time is you would expect to see the grades out. Is there any questions about quiz 1? Okay. So going back to the content, kind of like the last thing that we've learned in this class has been a 5-stage pipeline based on the RISC-V ISA. And so far you have seen that we have made quite a bit of improvement in terms of performance. We introduced the notion of pipelining, we introduced the notion of forwarding, we introduced a speculation with branch prediction, and we improved that branch prediction in various different forms. And then we also talked a little bit about compiler and software, but we didn't really delve into it. And we're not going to go to do that, but just keep in mind that that also exists. So now the question is, okay, what can we do in order to make the processor even faster, right? If you remember, we said that essentially the iron law of a processor was CPI times CT times IC, or the instruction count. So what we can do, and we have seen so far, and we have seen that it's effective, is adding more pipeline stages, right? For example, your quiz question was also like a deeper pipeline. And as I told you multiple times in the class, deeper pipeline is actually quite standard. So we can actually add more and more of these pipeline stages. If you add more pipeline stages, as long as you can feed the instructions into the pipeline, your CPI stays the same. You have smaller CT, so you get the benefit. But the problem is that with adding more and more pipeline stages, at some point you get what we call diminishing returns. The reason for it is threefold. One is that you get more hazards. As you have more and more pipeline stages, there are more opportunities for hazards, right? So, for example, in a five-stage pipeline, you saw that there is hazard between decode and execute, decode and write back, decode and memory, execute and memory, execute and write back. Now imagine that you have like a 15-stage pipeline. There is a potential, any sort of two, any permutation of the stages could result in a hazard. And then you need to add either like a forwarding logic for all of these, or you need a hazard detection unit. So your complexity grows significantly as a result. And then generally adding more pipeline stages add complexity in terms of power consumption and in terms of delay, as well as the additional delay for reading and writing these pipeline stages, okay? Another thing that happens is that if you add more pipeline stages, your penalties becomes higher. Your branch miss penalty becomes higher. Your load use might become longer. So all of those things actually happens as you add more pipeline stages. So at some point, really adding more pipeline stages not only helps you with increasing the performance, but actually degrades the performance. The reason for it is that your CPI is actually start to go up. And that's not what you want to happen in your system, okay? As I said, most of the modern processors dancing around somewhere between as low as 5 to like 15 or sometimes 20. And for really low-end processors, it's also possible to do like 3-stage pipeline. So usually we don't go below 3, but somewhere between 3 to 5 is like a regular for in-order kind of low-end processors. And for more modern processors, 10 to 15 is a regular number, okay? This is generally what we call a scalar processor. In a scalar processor where we do one data at a time and we do pipelining, the best that we can achieve is CPI equal to 1. We cannot get better than 1, right? Because if everything goes as planned, you get CPI equal to 1. And if you remember, I told you that IPC is 1 over, IPC is 1 over CPI. IPC is defined as instruction per cycle rather than cycle per instruction. If CPI is 1, obviously IPC is equal to 1. Generally, what you want to do is that your CPI goes down, or in other words, your IPC goes up. And also what you have seen is that in reality, your CPI is usually more than 1, right? Because of the hazards and mispredictions and so on. So we are kind of left with improving the CT as the only way to improve the performance. But there is an obvious thing that coming to mind is that why are we just processing one instruction per stage? So right now we have if you have a 5-stage pipeline, we have 5 instructions in the pipeline, 1 instruction per pipeline. Why don't we, for example, do 2 in the fetch, 2 in the decode, right? 2 in the execution, and so on and so forth. So you kind of parallelize the instructions within each stage as well. We have done so for each individual stage. Why don't we do it within each stage as well? Okay. And what we are actually now getting is what we call instruction level parallelism. So essentially, we are running 2 instructions at the same time. Okay, or 3 instructions or 4 instructions at the same time per pipeline stage, okay? And generally, this is parallelism or parallel processing is a very important topic in computer science. So far, what you have seen is what we call bit-level parallelism, which what we show that is that you can, for example, do 32-bit by 32-bit multiplication. You can read instruction 32-bit. These are all bit-level parallelism that we did. Now we are looking at instruction-level parallelism. You could argue that pipelining already give you a little bit of instruction-level parallelism because you're essentially what you're doing is you are kind of feeding the instruction into the pipeline and you're kind of overlapping these instructions. So we already did some level of instruction-level parallelism. But what we are introducing now is that you can actually run multiple instructions per stage, okay? Later on, we're going to see what we call data level parallelism and task level parallelism, DLP and TLP, when we're talking about multi-core stuff as well. So when we are actually running multiple instructions within the same stage, we call this a superscalar processor. So scalar processor is when you have 1 instruction per pipeline, and superscalar is when you have multiple instructions per pipeline, okay? So if you, for example, going back to like the simplified design that we have in our processor, if I, for example, want to have a 2 two issue, superscalar, where I can run two instructions at a time. Essentially, I need to add these red lines into my processor. So what is happening is that I'm basically fetching two instructions at the same time. By the way, this is your instruction cache or instruction memory, and this is your branch predictor. So I'm reading two instructions at the same time. So not only I bring the first 4 bytes, I also bring the next 4 bytes as well. So I'm reading 8 bytes at the same time. And then I'm feeding this to the register file. And since I need to process two instructions at the same time, now I need to read RS1 and RS2 for this instruction. I also need to read RS1 and RS2 for this instruction. These are two separate instructions, happens at the same time. So essentially what it means is that my register file now needs to have more ports, right? So remember your register file was look something like this, that you put the register number, right? You put the read register 1, read register 1, read register 1 and read register 2. And you get register 1 and register 2, right? Now, what we are adding is that saying that, okay, I need 2 more ports. So I kind of like extend this. I put 2 more, and then I get 2 more data here. So I get another reg 1 and another reg 2. And these could be independent. So for example, one of them can be X1 and X2. The other one could be X3 and X11. It could be also the same, doesn't matter. Since now I have the 2 of these, I also need to duplicate my ALU because I need to, for example, do 2 ALU operations at the same time. And then I need to kind of extend the wires back to the register file as well. So this is kind of like how your data path controller would look like. And of course, you need to then issue two set of control signals for this instruction, right? Because now you need to decode 2 instructions at the same time. You need to define this as well. One thing to remember, though, is when we have a superscalar processor, we cannot just double everything. So for example, we cannot double the register file. Why? Because if you double the register file, then you're going to have inconsistency issues, right? Like if you say, okay, there is RS1 for register file 1, and there is RS1 for register file 2, and then sometimes you need this and sometimes you need the other one, then you're going to have what we call a consistency issue, which, these copies are not the same copies. Same issue with memory. And on top of the consistency issues, it's going to be extremely expensive in terms of power and area if you want to duplicate the number of registers that you had or duplicate the number of memories that you have. So we cannot like duplicate everything, but we duplicate things that we can duplicate. So for example, we duplicate the ALU, we add more ports to the register file and things like that. Yes. Yeah, so the question is, for a superscalar processor, for example, for this 2 issue 1, we cannot support 2 memory at the same time. I can still add more memory ports. So for example, I can support 2 access requests to the memory if I have, for example, 2 address ports and 2 read ports. Or maybe I can do read and write at the same time, right? Because read and writes are 2 separate things. So there are these tricks that I can do. But yeah, there is a limit to it. I cannot just duplicate the memory storage itself, right? So that's the point that we are trying to. Yes. Yes, the stuff that actually works with data doesn't require storage can be duplicated, right? Like you can duplicate wires, multiplexers, pipeline registers, controllers, branch predictors, all of that. But register files and data, you don't. But you add ports. You can add more ports to the register file. That's fine. Yeah. Yes, the ALUs could be identical or could not be identical. Later on, when we are talking about out of order execution, you will see that we have what we call functional units. And functional units could be different things. So for example, there could be functional units that just doing adding and subtraction. There could be functional units that doing multiplication. Actually, when you have these functional units, then you can schedule them properly. But for now, yes, you can assume that these are identical. So they can do everything as if they want. Otherwise, you need to kind of decide, okay, which one do I need to use? And some form of like a decision needs to be made. All right. So another thing that you don't want to duplicate is the PC, because essentially all you can do, everything you can be done with just one PC, right? As I said, what you can do is essentially your PC. Currently, what you were doing for one instruction was you were basically reading 4 bytes and then put this as one instruction, right? So this was one instruction. What I can do now is that this would be my instruction 1. Then I will continue, right? PC plus 4, PC plus 5, PC plus 6, and PC plus 7. And that would be my next instruction. So I don't need to maintain 2 PCs. I just need to read them. So I need a bigger port. So I need a bigger bandwidth to read things, okay? And then, of course, I need to change the logic for the next PC. So next PC should no longer be PC plus 4. It should be PC plus 8. Okay? Excuse me? Yeah, and then, so these questions I already answered. For example, your ALU could be used, one of them could be used for R-type instruction. The other one could be used a special purpose for just adding and subtraction. Remember that for BEQs and store word and load words, all you needed to do was adding or subtracting. So these two ALUs does not need to be identical. One of them could be simpler, but you can also make them identical, so it doesn't matter. So yeah, in that case, for example, in an ideal scenario, you would have something like this. Now, for example, let's say you have a load word and add, then you have a sub and add-I, then you have a store word and add-I. And what would happen is that essentially the way this would work is you put the load word and add at the same time into your instruction memory. Then in the next cycle, load word and add goes into the second cycle. Sub and add-I comes in, and then load word and add goes to the next cycle. Sub and add-I comes here, and then you fetch store word and add-I, and so on and so forth. So this continues, right? Yes. Yes, of course there were going to be hazards. I was actually going to ask you, what are the problems you're going to see in this design? The first one could be hazard. What type of hazards you're going to see? You're going to see read after write, but then would forwarding fix this issue? Why not? Okay, yes. So the interesting thing is that I still can forward, for example, if this instruction is somewhat dependent on either of these two instructions, I can still do the same forwarding as I did before, right? I can forward from here to here. Basically, I forward from here to here or from here to here and so on and so forth. So forwarding from previous instructions to the next instruction still can be done. The logic would be slightly more complicated because now I need to forward from one lane to another lane and so on and so forth, but it's possible. What is not possible, though, is that if there is a dependency between this instruction and this instruction, because they are both in the same cycle. So the result is even not generated if you want to go back and do the forwarding. So this would not be possible, okay? Any solution to fix this? Yeah. You can reorder instructions if possible, right? So for example, let's say if this instruction is somewhat dependent on this instruction, if I somehow, for example, I find this guy and move it here, then I can fix this issue. So reordering can help, but reordering, remember, for forwarding could also be helpful, but we said that compiler can actually do the reordering. But the problem is that the compiler needs to do a lot of checks, and it would be difficult for the compiler. Yes. Good question. So stalling in this case would have been that, for example, we see a load and an add, and we see that, oh, add is actually dependent on the load. So what you would do is that you essentially create some form of a bubble, same way that we created bubble. So when we are feeding this into the pipeline, what we are actually feeding is this. And then what we do next is the add and the next instruction, whatever it is, like add and sum, right? So this will fix the problem. So essentially, I'm not, in other words, I'm kind of like, I don't even need to feed the bubble. I just don't feed anything to the pipeline, right? So I'm not utilizing my lanes. These are, by the way, usually called lanes. I'm not using all of my lanes at the same time. So my utilization is, for example, in this case, 50%. So I go back to the CPI equal to 1. In this case, if everything goes right, my CPI would be 0.5, like 1/2. But worst case, I go back to 1. What else? What other problems are going to see in this design? Yeah. Loading and storing issues might be also a problem, especially if you don't have enough ports. So we're going to run into what we call structural hazards, right? So remember I told you that in the original design, we didn't have structural hazards because we have enough ports. But if, for example, load and store needs to run at the same time and we don't do it, we cannot do it in parallel. If we have scenarios where we have a load word and store word in the same cycle, then we may not be able to do it. Or we have like 2 back-to-back loads, maybe we cannot do it. Okay. What else? Branches. What about branches? Nothing. The instruction. Yes. So branch or control flow divergence becomes even more challenging, right? So if I have a BEQ and then another instruction, right? So an add instruction, by the time that we realize that we made a mistake, the add instruction is already kind of like at the final stages. So my flushing logic is fundamentally different. I still can flush future instructions, but it's going to be very difficult to flush this instruction, right? And also my penalty becomes longer because now any wrong decision kind of flush. Let's say if I do it in within one cycle, I flush 2 instructions instead of 1 instruction. So my penalty is also growing. Any sort of flushing would be 2 instructions. You have a question? Okay. So yeah, so I'm kind of just summarizing what I said. So Superscalar is great and it's being used, but there are challenges. The first challenge is the dependencies. We can add forwarding for between 2 groups of instructions, but we cannot forward within the same group of instructions. Okay. Uh, and then this problem becomes worse if we actually increase the number of lanes. So for example, if you have 4 issue processor or 8 issue processor, then we're going to have even further problems in terms of dependencies, because now the likelihood of dependencies grows significantly, because any 2 that has a dependency, we're going to run into a problem. Okay. So for example, for 2, what you need to do is basically you need to check, to perform 2 checks, right? So you need to make sure that the destination of this guy and the source of these other guys are not the same. But then when it becomes 4 instruction, now you need to check these 2, you need to check these 2, you need to check this, and then you also need to check this with this one, and then this one, and then you need to check this with this one, and so on and so forth. So there are many checks that needs to be done. So if the compiler, for example, wants to decide whether or not these instructions are dependent to each other, there's lots of checks needs to happen. Even in hardware, this would be very problematic and very time consuming. Yes. Say louder. Okay. Okay. Is it better? Okay. So I need to do a little bit more checks if you want to. And then this becomes easily very problematic in terms of runtime. Modern processors typically use 4-issue pipelines, sometimes even 8-issue pipelines. So just keep in mind that four-issue superscalar is kind of like standard in modern processors. Okay. So kind of like to summarize, the good thing about Superscalar is that it's giving you a higher IPC or lower CPI. But the disadvantage is that it has higher complexity because of the dependency checking, and it requires obviously more hardware, right? So that's the problem. As a result of these dependencies, excuse me, typically we have what we call underutilization. Underutilization means that I can, for example, issue 4 instructions if I have a 4-issue pipeline, but because of the dependencies, for example, I decided not to issue 2 of them, right? So this means that I'm wasting cycles and wasting instructions. So that's one issue that we're going to see in Superscalar processor. But generally, when I combine use Superscalar with proper forwarding, I'm gonna get IPC more than 1 or CPI less than 1. Okay. So that's kind of like the summary, but there is a big issue, and that is the dependence that we need to do. And then if you think about dependency, the reason that we have dependency is we need to stick to the program order, right? So essentially I say that, okay, I need to fetch these 4 instructions, and I need to basically check, oh, this guy and this guy, this guy and this guy, this guy and this guy, do they have dependencies? Okay. But what if that I tell you that you can actually look into the larger window of instructions, and then you basically can pick whatever 4 instructions that are not dependent to each other. So if I can come up with a mechanism that I can dynamically look at the larger window of sequence of instruction and have a mechanism to be able to check this dependency very quickly and pick the ones that are independent of each other and feed it to the pipeline, then if this search is large enough and long enough and fast enough, then I can always find 4 instructions and feed it to the pipeline. Okay? That would be the idea of what we're going to talk about out of order execution. Basically, we are relaxing the requirements of things needs to be right after another and allow the search to grow significantly in a window of instructions, find the independent ones and feed it to the pipeline. Okay? So that would be basically the idea of what we call out of order execution. Any questions so far? Yes. At some point, you would, so I mean, even for the out of order execution, you would at some point need to stall. So is that a question that at some point you would need to stall the processor? Yeah, so I mean, of course, pipeline, as you're going to see that there will be mispredictions, so you need to flush. There will be other issues with the pipeline, but you get closer to IPC equal to 4. That's what we're trying to achieve. You're never gonna get to exactly 4. Did that answer the question? Okay. So we're gonna start talking about out of order execution. So the idea of out of order execution is the following: that instead of finding the next, executing the next instruction, let's find the first available instruction and execute that. What is constituted as availability? We're going to talk about it later, but generally availability means that I have units, I have pipeline lanes that I can issue this instruction to it, and this instruction does not have control flow or data flow dependency to the previous instructions. If these criteria are met, then I can issue that instructions into the pipeline. So I need to basically maintain a window of all the available instructions, and then I pick them and kind of feed them into my pipeline. That's the main idea of out of order execution. If this window is large enough and we can always find and fully utilize our pipeline, then essentially our IPCs becomes equal to n, which n is the number of lanes, and super is the number of issue of the superscalar. So if I have an 8-issue superscalar, I can have an IPC of 8. Okay, so that's how you actually get performance in this systems. So there are actually lots of questions when we say this. So first of all, how do we know what is available? How to find them? How do we keep track of them? How do you update something of availability? Now that we are kind of like saying that, okay, things can be run out of order, does that create new problems in the processor? Does that create new hazards? What about branches? What about raw data hazards? Are there new hazards? What about memory? What about branch misprediction? So there are lots of questions that basically comes in mind when we are talking about out of order execution. For the rest of this lecture and lecture in Thursday, we're going to basically cover those things. Okay? So let's dive right into it. Essentially, in order to achieve out of order execution, you need three things. Three main ingredients of your out of order execution are these three things. So we're going to first focus on these. Then I'm going to give you a little bit more kind of like, additional trade-offs and design considerations and so on and so forth. Okay? So we need first, oh, you had a question? With correctness. Yes, we're going to actually have that, right? So we need a mechanism for recovery as well. So if you make some mistakes, you need to go back and fix those mistakes. So you need three things. You need a mechanism for tracking instructions. Essentially, instructions needs to be tracked so that you know that this instruction is available, which means that there are no longer any dependency with this instruction and any future previous instructions. That's when that instruction is ready and it can go into the pipeline. And since this is a dynamic thing, we need a dynamic mechanism for this readiness tracking. So, for example, one instruction might be dependent on the previous instruction. Once that previous instruction is finished, then you can feed this into the pipeline, right? So you need that mechanism for that. The second thing that we need to do is that we need to be able to fix the data hazards. The same way that we fix the data hazards for our in-order pipeline, we need to also fix the data hazard for out-of-order pipeline. Interestingly, for out-of-order pipeline, since we are running things out of order, we're also introducing new hazards. This will be write after write and write after read hazards. We're also going to have problem with memory because if I reorder the instructions for the memory, then I'm going to also have problems. So there are things that I need to basically fix there. And finally, as you asked, there are going to be challenges with especially control flow, especially branches. But as you're going to see, we're going to actually introduce even more speculation. So branch is going to be just one of them, but there's going to be also other cases that we make some prediction and do something based on that prediction. And that predictions could be wrong, and we need a mechanism for recovery. And recovery for an out of order is significantly more complex because things are not in order anymore. Okay, so we need to fix these three issues. Let's talk about each one by one. So this would be our design of the processor. When we are saying when we are saying out of order processor, our out of order processor are essentially three parts. Okay, there is what we call a front end. Okay, the front end of the processor is when you're fetching and decoding instructions. You're still fetching and decoding instruction in order. Okay, in order to keep track of things, you still need to maintain the order of the program. So the front end of the processor, even for an out of order processor, is still in order. So you read things one by one from the instruction memory. Okay, then you execute things out of order. This is usually called the back end of the processor. So there is this thing called execution, and there is this thing called completion. And I'm going to talk about why we have these different things. And then when we are complete and execute this instruction, we reorder them back into the order that they were supposed to be. So the same order that we read them, we reorder them back. So think about this kind of like, you're mixing and matching, But when you're putting it back, you're putting it back to the place that it was. Think about like books in the library that's like a nicely kind of like organized. You can pick any one you want, but when you're putting them back, you're putting them back in the place that they were. You don't put it at the beginning or at the end, okay? This is called retiring the instruction. I'm going to formally define what is a retirement, but we're going to retire in order. So generally, an out-of-order processor is a sequence of in-order fetching and decoding, out-of-order execution, and in-order retirements, okay? So keep that in mind. So let's first talk about the last problem, which is the pipeline recovery, because that's kind of important for everything else. So we want to talk about that, okay? So let's just start with an example. And let's say I have a sequence of instruction I1, I2, I3, I9, all the way to I9. This doesn't matter which ISA you're using. It could be RISC-V ISA, so this could be add and load and whatever. Could be other pipelines, okay? So let's say, for example, there are a sequence of instruction, there is a pipeline, and there is a completed instructions, okay? In an in-order processor, things are straightforward, right? So you read them one by one, you execute them by one, and you complete them in order as well, okay? So for example, you start with like, you start with I1, I2, I3, I4, I5, you fetch them, fetch, decode, execute, so on and so forth. So at some point, for example, I1 is completed, I2 is completed, I3 is completed, and then in the pipeline, you have I4, I5, I6, I7, and so on and so forth, depending on how many stages of the pipeline you have. And let's say in this scenario, for example, let's say your I4 was a branch, okay? And it's a branch that is decoded, the outcome of the branch known in the memory state. So 3 cycles of flushing needs to be done, okay? So in an in-order processor, let's say that we decide that I4 is a branch instruction. As a result, I need to basically flush I5, I6, and I7. We already discussed how we can do this. We replace it with the bubbles and so on. But then basically the flushing is straightforward. You flush them, you go to, let's say, for example, whatever instruction that you're supposed to run next. Let's say, for example, you need to run I8. You fetch I8 and you continue. Nothing bad happens. You already know how it needs to be done. Okay, but let's actually talk about the out of order execution format. In out of order execution format, you can actually fetch instructions, but when you're actually putting them into your execution pipeline, you can put them in any order that you want. For example, you might actually end up doing something like this. Let me actually put the example here. So you might have like I1, I2, 3, 4. I'm just putting the numbers to make things simpler. 6 and 7. And then when I'm actually putting it into the pipeline, maybe I do something like 1, 2, maybe 3, 4, 5, and 6 are all dependent to 2. So I cannot feed them into the pipeline. As a result, I actually put 7 into the pipeline. Okay? And then what will happen is that after some time goes, these guys will get into what we call a complete. So these instructions will be completed. So 1 goes here, 2 goes here, 7 goes here. And then, for example, once 2 is completed, let's say I can now fetch 3, 4, 5, and 6. Okay, so I can fetch these instructions as well. And similar to the previous example, let's say 4 is actually a branch. And then I realize that I do a misprediction. So I need to actually realize that, oh, this is a misprediction. So I need to flush everything after, right? When I'm flushing everything after, I can easily flush 5 and 6 because they are in the pipeline. I can issue the same bubbles. But what I cannot flush is 7 because 7 is already gone. It's already completed. It's already executed and left the pipeline. So I'm going to run into a problem where I need to flush things, but since I run things out of order, I already executed that instruction. And that's going to be a big problem for us. Okay? So this is the example. I want to flush these guys. I cannot flush. And I have this problem that I7 is already completed. I cannot flush it. Okay? So in order to fix this problem, we define this concept called retirement. And then we separate this from the notion of executing an instruction, okay? So when we are doing this, since basically what we need to do is that we need this I7 to somehow still exist in the pipeline so that if we need to flush it, we can flush it. So what we do is that we define two concepts that are different from each other. We define the concept of what we call an instruction is complete. Then we define a new concept called instruction that is retired. What's the difference between retirement and complete? Complete means that I write it only into a temporary registers. I basically just write it into some form of a buffer. I only write it to a permanent storage, which is permanent in our case is the register file, is a register file, my data memory, and my PC. These are my permanent storage parts. I only things into my register file, my data memory, or my PC when I'm sure that this instruction is not going to be flushed. Okay? How do I know that this instruction is not going to be flushed? When all the previous branches are all resolved. Okay? So when all the previous instructions has been resolved and executed, when this instruction is the last instruction that has been completed, then I can quote unquote retire these instructions. And retirement means that whatever we wrote into that temporary buffer, we write that temporary buffer into my permanent buffer. Okay, so this is what we call a retirement, or in other terminologies, people also call this commit. So if you heard the word commit, it's the same as retire. So we usually use the word retire, but some other references use the word commit. Okay. So when the instruction is finished is when we are actually writing things into permanent storage. In our in-order processor, we had this as write back. So write back is basically equivalent to the retirements in an out-of-order execution. But the step before that is complete when you're kind of done with that instruction, but only store it in a temporary storage. Okay? So as I said, writing back to the register file, or writing back to the data, or updating the PC. These things, if I do it, I cannot flush. But if I write it into some temporary buffer, all I need to do is flushing that temporary buffer. Nothing bad happens. Okay? So essentially the idea becomes like this, that I complete things out of order. I don't need to be worried about, oh, this instruction needs to be flushed or that instruction needs to be flushed. I can just execute anything that I want as long as there is no dependency. I write it into some temporary buffer called reorder buffer or ROB. And then I only write it from that ROB back into my register file, PC, and data memory when I know for sure that this instruction is not going to be flushed. Okay, this is usually what we call architectural states. I think I said this before. So architectural states are these permanent storages. Okay, so I write things into my buffer, which is my macro architectural state, but only visible to architectural states when we know for sure that this instruction is not going to be flushed. Why this would work? So now you can clearly see that if I have another row that called retire, okay? So in this particular example, I can retire I1, I can retire I2, but since I7 is still waiting for previous instructions, I don't retire I7. I wait until I6 becomes completed, and that's only when I can retire I7. So in this particular case, when I realize that, oh, I4 needs to be flushed, the things that I'm going to flush is that everything in the pipeline plus everything into the completed queue. So I can basically flush all of those things from the completed queue, and I can start from a fresh set of instructions. Yes. Yeah.
Execute future instructions. The work that instruction when, like, let's say that it based on someone.
Good question. So if I'm writing into temporary memory and then there is a future instruction that is somehow dependent on this instruction that is completed, what should we do? There are actually two ways you can do it. You can always refer back to your retired instructions. So you don't read it from this temporary memory, you read it from the permanent memory. That makes things slow because you already have the results, but you're not using it. But it's very simple. But in most cases, it's similar to the forwarding logic. So you forward it from the complete back to the execution. We're going to actually talk a lot about this later. Yes. Good question. So the question is, if I'm pipelining and then like, so in this particular case, for example, I3 doesn't need to be flushed, right? It's because even before I4. So why are we flushing I3? You can actually have, there are actually mechanisms for keeping track of the age of the instructions and then decide. But keep in mind that this makes the pipeline slightly more difficult to track, right? So now you need to also check the PC and then only insert bubbles under certain conditions, but it's possible. Yes. Yes. So the question is, when exactly decide to retire instruction? I actually, in the next slide, I'm going to show you that. Okay. Let me actually, I'll go back to this. So how to implement the retire? We need, as I said, a buffer or temporary storage. And then we need to also track a mechanism on when is the good time to retire things, right? So for this, we introduce what we call a reorder buffer, or ROB, or ROB, some people call it. ROB is basically a circular buffer that what it does is that it's temporarily store the information related to one instruction, okay? And the condition for retiring an instruction is when all the instructions prior to that instruction is already retired, okay? So we kind of retire things in order. So we can only retire 2 when 1 is retired. We can only retire 4 when 3, 2, and 1 is retired, and so on and so forth. So we only retire things when all the previous instructions prior to that instruction has been retired. How do we know which instruction is 1 or 2? We use the PC. So PC will be basically a mechanism for you to decide which instruction is older than the other instructions. So you only retire instructions when the PC of all the previous PCs are retired. Okay? So how do we keep track of it? So reorder buffer kind of looks like this. We usually have what we call the head of the ROB. So a head of a ROB is a pointer. Okay? So a head of a ROB, for example, is like this. And since this is a circular buffer, you usually also have a tail. So you have a tail and a head. But for now, let's say that this is a linear one, so you only have a head. So you retire an instruction when the instruction is the head of the ROB. So for this case, I can retire this instruction. I cannot retire this instruction because the head of the ROB is here. And whenever we are retiring an instruction, I move down the head of the ROB. So the head of the ROB basically goes here, okay? So this would be head of the ROB. This instruction is available, so I retire this instruction. I then move the head of the ROB here. I can also remove this from the table. I no longer need to use it. I can reuse that space for future instructions. But then I cannot retire these instructions because retiring this instruction means that I need to first retire this instruction. So head of the ROB is here. The instruction is not available yet. So I don't retire anything here. I wait until this instruction comes. Once this instruction comes, and then by the way, when I don't retire this means that I don't retire this or any other subsequent instruction. I don't retire anything until I reach to the point. So when I2 comes, then I can retire I2, and then I can decide to whether or not I can retire more instructions. How many instructions can I retire per cycle? That's the design of that depends on the design of the processor. Some processors can retire multiple instructions at the same time. Typically, the same number of instructions that you can read you want to be able to retire the same number of instructions. So if I can read 4, I would retire 4 at the same time, and so on and so forth. Typically, you retire less. Sometimes you retire less than the number you can issue because instructions takes more time to get in. So you don't want to retire. But usually, as a rule of thumb, if you have, let's say, a 2-issue processor, you read 2 instructions and you retire 2 instructions at the same time. So for example, in this case, if this is a 2-issue, I would retire this instruction and this instruction, and I move the head of the ROB to here. In the next cycle, I would retire this instruction. Okay? And then if I need to flush, so if I go back here, if for example I2 is a branch instruction and it never actually retires, and we issue a flush, what we will do is that we basically invalidate everything below that instruction. So all these instructions that were completed are all invalidated from the ROBs. They are removed from the ROB. That's all we need to do in order to make sure that we are flushing instructions properly. Okay? So what exactly do we store in this ROB? We're gonna later give you like a more detail, and then basically this will be your CA3 when you're designing an out-of-order processor. But there are many things that you need to store. You need to store the PC. You need to store the data. You need to store register numbers. You need to store the value of the registers. The reason for this is that for recovery, you need all this information, because if you make a mistake and you need to go back, you need to basically put the processor in the checkpoint points that it was valid before. So you need to kind of store a lot of things in the processor. Okay? So so when I show you the ROB, when I show you this thing, this is actually have multiple entries within the same row. Okay? Just keep that in mind. Okay? Any questions? Yes. How large is the ROB? That also depends on the type of the processor. Typically 96, 128, that's usually the size. Keep in mind that if your ROB becomes full, okay, then you stall the processor. So all of these queues, as we're going to talk about them one by one, any of them that becomes full, you stall the processor, you wait for the instruction that is dependent to reach to the end of the ROB, and then you can issue new instructions. Any other questions? Okay, let's have a quick break. We're going to come back and talk about this. All right, moving on. So your CA2 will be released today. It's going to be a competition, as I said at the beginning of the class in lecture 0. It's individual. There is a leaderboard that you basically design your branch predictor. There is a metric. You put your metric there. Whoever has the lowest will be higher in the order, in the ranking. The way that we're going to grade this is that CA2 is completely optional. It's a bonus. So if you don't turn anything, you don't lose any points. You also don't get any points either. You don't get any bonus points. For everybody else who is submitting something, if you end up in the top half of that leaderboard, you're going to get some bonus points. If you end up in like top 10%, you're going to get a little bit more bonus points. If you're in top 5 or whatever, you're going to get more bonus points. So the list is in the description. Okay. So if you put more time and do a better design, you get a little bit more points. But these are all bonus points. So if you don't submit anything, you're not losing anything. If you submit your CA1 and CA3, get 100 points off of those, you get the full grades for your CAs. Okay. Yeah, and then more details will be on the branch and the description. It's going to be released today, and I think deadline would be next Saturday or Sunday. And since this is a competition, we're not going to do any extension and or late submission. So you either do it by that time or you don't do it. Okay? Yeah, and then further questions. There's also, I recorded a video of like how to design, do the branch predictions. Also asked the LAs and TAs to talk about a little bit about that in the discussion section. So feel free to go and ask questions there. And yeah, okay. So hopefully, so this is more of a for you to kind of explore a little bit more on the branch prediction if you're interested. So it's more of like a researchy, more kind of like, do it in your own time if you're interested kind of project. And then CA3 will be on designing the back end of an out of order execution, which is going to be released the following weeks after the branch prediction deadline. Okay. Discussion sessions, as I said, the attendance is no longer required. Everyone will get the bonus. For now, we're going to do the 3 following sections that I'm showing you here. We will add more if there is attendance. If not, we're going to keep this. If you cannot make it, message me and we can definitely schedule one-on-one with the TAs and LAs, and you can ask your questions. So you're not going to miss anything if you're not be able to attend this. But message me so I can have a list of people who potentially interested, so we can add more discussion sections. During the discussion sections, they will go over a worksheet. They're going to discuss relevant topics. As I said, for example, this week will be about the CAs and so on. Any questions? Yeah. Both the TAs and LAs will be there. So you will see, you can see them both. So so all of these discussion sections, there are both TAs and LAs. And actually the reason that we changed the format is we require both TAs and LAs to be available. We initially thought that only LAs should be available, but there are some complications with unions that TAs and LAs should be on all discussion sections. So that's why we're changing it this way. Okay. Perfect. Going back to our retirements. So we need to store a bunch of things. And as I said, you're going to see exactly what you're storing where when we are giving you a concrete example in the lecture. And when you're actually implement this similar way that you implement your CA1, you're going to implement this in C code. You're going to actually see the entries that you need for your design. So you're going to see the details there. So if I want to kind of update my 2-issue superscalar processor with an ROB, this is how it would look like. Okay, so essentially what will happen is that I'm basically disabling this write back from my design, and what I'm going to do is I'm basically writing everything to ROB, and I'm also writing everything like in terms of like the instruction and branch prediction into ROB. And ROB only write things to the register file and write things to the data memory and write things to the PC. Okay, so write back is basically not the same write back that we had before. You write it to the ROB as a temporary data structure, and ROB decides when to write things into this permanent storage units. Okay. And then this was your data path without the ROB, obviously. Okay, so going back to this table that I'm showing you here, just bullet points, I already talked about kind of like this last one. So if I know how to recover things. How do I detect and when do I detect misprediction and all? That's a question that I'm going to talk about later. But let's say somehow I figured out that there is a misprediction, there is a reason for flushing the pipeline. I can now know how to flush the pipeline even if I did it out of order. Okay, so let's talk about the other two. Let's talk about this one. So what will happen when we are doing out of order execution? What are the dependencies that we are seeing and what are the new dependencies that we're going to see? So remember that in order processors, we had what we call a read after write or raw data hazard. Raw data hazards was when we had something like an add x2, x1, x3, and then we have a sub x4, x3, x2. There was a raw data hazard between x2 here and x2 here, and we said that we need to fix it with forwarding. When we are actually doing the out of order execution, so if somehow we decide that execute sub before add, we're still going to have the raw data hazard, right? Because here, this value of x2 should have been the value produced by add, right? So if I actually execute x2 before, execute the sub before the add, I'm going to run into problems, right? I'm going to run into correctness issues. So I should not allow this to happen. So same issue that we had in order, we're going to have in out of order. We should not let sub to execute before add. Okay? This is what we call a true dependence. This is a raw data hazard. Then we're gonna run into new issues as well. And remember, I told you that these are not issues in order because we run things in order. But when it comes to out of order, we're gonna have those problems. So here they are. So we have the right after right issue as well. This is what we call output dependence, if you remember. And this is when we are having the same destination register written twice. So for example, an add instruction writes to x2. I have a subsequent sub instructions also writing to x2. The problem here is, though, that if I reorder these things, I'm going to have a problem because this sub should be happen after the write to x2 from the add. So timeline wise, the programmer assumed that this is later, but if I reorder the execution, this is not going to be later. This would be the later result. So again, this will result into correctness issues. And finally, if I have a write after read, which I'm basically reading from a register and then later on writing to it, for in order this wasn't an issue. But again, if I do this out of order, you will see that essentially x2 here is being written, but later on it's being read. In the original one, this value was supposed to be read from the previous values, and this is later is going to be updated. But as you can see here, that the value is updated by sub, and it directly impacts the value you're reading for the add. So this is also a problem. You should not allow this to happen. Okay? So long story short, you're going to have the problem of three types of hazard. You have a raw data hazard, which you used to have in order. You will now have write after write data hazard, and you're going to have write after read data hazards. The write after write and write after read is called output dependence and anti-dependence. The good news is that output dependence and anti-dependence can be easily fixed. Okay, I don't need to do extra things to fix them, and I'm going to show you how you fix them. The raw data hazard one is still going to be an issue, and we're going to show you a more elaborate solutions of how we fix it in out of order execution. But let's actually talk about how do we fix these two issues. The fix for these two issues is basically very simple. So imagine that instead of x2 and x2 here, one of them was x5. And then as you can see, there is no dependency in terms of reading the values here, right? I'm writing to a register, which is x2. Later on, I'm writing to another register, which just happens to be also x2. If I change that x2 to x5, nothing happens, right? In terms of the performance of correctness of the system, as long as I know that that one is x5 and that one is x2, nothing's going to happen. Same story here, right? So if you look at this, this is the source, this is the destination, right? If I change this destination to another destination, to x5, x7, x8, then even if I do it this way, it's not going to be an issue, right? So essentially the destination registers, if these two are truly independent from each other, I can just change the destination registers to other registers. This is a process that we call renaming. So we essentially rename the destination registers of our processors. If you have other available registers, what I can do is that instead of using the same registers over and over, causing this reordering to become challenging, I use other registers, right? I use other available registers, rename this registers to that registers, and move on, okay? This is what we call renaming, and the difference here is that these are not true dependence, which means that it happens only just because that the compiler decides to use the same two names for the registers. I can just use other registers, and boom, this will be fixed, okay? So how do we do register renaming? in order to know how do we do register renaming, there is another concept that I want to point out, and that is the difference between what we call architectural registers and physical registers. Okay? So architectural registers are registers that we use for a given ISA. For example, for RISC-V, I told you that we have X0, X1, X2, all the way to X31. We have only 32 architectural registers. If I have the best processor in the world, I still have only 32 architectural registers. Why can't I use more architectural registers? Because changing architectural registers means that you need to change the pipeline, you need to change the ISA, right? Because in the ISA, if you remember the machine code, which probably forgot, like you had the opcode, and then you have like RS1 here. And RS1 was only 5 bits, and it was 5 bits because you only had 32 registers. If I want to decide that, oh, you know what, I want 64, then you need to change this. And if I change this, I need to change the rest. And if I change the rest, I need to change the entire microarchitecture. So I'm kind of frozen in terms of number of architectural registers that I can have. This is not what I'd like, okay? So in order to fix this, I introduce a new concept, and that is called physical registers. Physical registers could be any number. Could be 628, could be 256, could be 1024, depending on how much budget do you want to assign to your register file, to your physical register file. Then you can have bigger and bigger registers. Physical register files would depend, the size would depend on the class of the processor. If this is a low-end processor, you probably want to stick to the 32. You don't want to go beyond that. If it's a high-end processors, you go beyond that. Okay? So now that we have this different notion of what we call A-reg and P-reg, the architectural registers and physical registers, now we need to find a mechanism for mapping these two. So essentially what will happen is that since I have many more physical registers compared to the number of architectural registers, one architectural register might be mapped into the multiple physical registers. And that's kind of what goes back into the renaming logic. So now what I can do is that the trick is I can assign 2 different physical registers to my X2 in this example here, right? So if the first one is assigned and mapped to one physical register and the other one is mapped to another physical registers, no problem at all. I can just, from then on, I can just use the physical registers and move on with my life. I can reorder things. I can do whatever I want with them, okay? This problem, though, I cannot fix, okay? Because this is what we call a true dependence. This is indeed physical or architectural. These are actually dependent on each other. So I cannot say, oh, you know what, this would be physical register 3 and this is physical register 2. No, that's not true because these are actually dependent on each other. But these ones, this can be P5, this can be P2, or whatever number they want. Just a map, okay? So this is the idea of renaming logic or renaming. And what we do is that we essentially introduce during our decode stage a step called renaming step, okay? So during the decode, we introduce a new pipeline stage that is basically what it does is that it reads the instruction, look at the A-reg, and then do the mapping to the P-reg. And from then on, it just, you know, like deal with the P-reg and continues forward. How do we do that? Use this thing called RAT. This is called Register Alias Mapping Table, okay? Essentially, the way it works is that RAT is a table that has 1 row per architectural register. So for example, if I have 32 registers, I have 32 row in this table. And then what it says is basically the current and previous mappings of for example, X0, X1, and so on and so forth. So here I basically keep track of the mapping between the A-reg and P-reg. And I might have multiple mappings, so I might need to have multiple entries in this table, okay? Usually what we're really interested in is the most recent one. So that is like, what is the most recent entry of this table? And that's what we usually store in the RAT itself. The previous ones, usually we store it in the ROB, as I'm gonna explain later, okay? So using this rat table, then we're going to do our renaming logic. Our renaming logic is the following. For each destination register, for each destination areg, we find an available preg and assign a new mapping between areg and a preg. For all the source areg, we just look at the current mapping and use that map. Okay, let me actually give you an example so that you can see it. So let's say we have 5 architectural registers and 10 physical registers. I'm just picking a subset of, let's say, RISC-V that we had, okay? So my rat going to look like something like this. That, as I said, I have 1 row per architectural register, and we basically keep track of the latest PMAP physical mapping of this, okay? In addition to that, I have another table called free pool. This is basically the pool of the registers that are free. What does it mean to be free? It means that you're not assigned to any of the registers, okay? So initially, let's say that your mapping would look like this, okay? The mapping could be this, could be any other mapping, but let's say originally X1 is mapped to physical register 1, your X2 is mapped to physical register 2, and so on and so forth. As a result, your P6, P7, P8, P9, and P10 are not mapped to anything. And for now, let's ignore X0, okay? So I'm starting from X1. So I have an initial mapping like this. Let's see how our renaming logic works, okay? So let's say I have a sequence of instructions like this. I have an OR X3, X2, X1, then I have an add, then I have a sub, then I have an add-on. So let's see how do we do the renaming? So remember, renaming basically is part of your decode, okay? So you fetch these instructions, you want to decode them to see what they're doing. Here, you also kind of update this map, okay? So how does it work? So the algorithm, as I said, is the following. For any source register, I look at the current mapping and I use that mapping. For any destination register, I issue a new mapping, okay? So I'm gonna do this for this first instruction. So this mapping would be like this. So what is the current mapping for X1? It's P1. What is the current mapping for X2? It's P2. And I need to issue a new mapping for X3. So the current mapping is P3. I'm gonna change that to a new mapping. How do I find a new mapping? I go through the free pool and I pick one of them. I can start from the top. I can pick randomly. I can do whatever I want. Let's say I pick from the top. So I pick P6 and I put P6 as my new mapping, okay? So now the new mapping between X3 is P6, okay? Do I put P3 back here? Not yet. There is a mechanism for freeing the registers, and you only free registers when you're retiring the instruction. So you don't immediately put P3 back into the free pool because this P3 is still in the pipeline because this instruction is dependent on some previous instructions that they might be still in the pipeline. You only free P3 when all of those previous instructions are free, okay? So just keep that in mind. So let's continue. Now I have my add instruction. So same idea, source, I use the current mapping. So for this case, X4 is P4. X3, the current mapping is P6, okay? And X4 is the destination. So I create a new mapping. So I put P7 and I put P7 here. Keep in mind that, this instruction, if you actually pay attention to it, you see that the source and destination is the same, but their physical registers are different, okay? So it just means that, X4 is read from P4, but now the destination is mapped to a different register. So this is because I have multiple physical registers, so I can actually use this luxury in order to reduce the kind of like, the number of collision between the destination registers, okay? So you guys tell me what would be the next one. So actually, let me go down. So, okay. So just repeating what I said, P1, P2, or would be P6. So I'm going to change this. I'm going to remove this from the free pool. This one again, X4, X5 would be P4, P6. I need a new mapping. I take P7. So I put P7, I remove it from the free pool. So let's see what would be the sub. Anyone wants to say what would be the sub? So sub, what is X2? Yeah. Yeah, you have a question? Go ahead. Yes, it's run before, it happens during the decode. Okay? Yes. Any other question? Okay. So what is X2? P2. What is X5? P5. What should I put for X3? P8, right? So this is gone. So I move this to P8 and I put P8 here. Okay? What about add-I? So add-I. What should I put for 2? It's the same immediate. So you don't rename immediates, right? Immediates are immediates. What about X3? P8. And what about X1? P9, right? So it's kind of like, you remove this, you remove it from the free table, you look at this, you go to the next one, you remove it from free table. This would be basically your final table. Yes? Yeah. Yes, yeah, if the number of issuing, for example, if you issue 2 at a time, you do it for 2. If you issue 4 at a time, you do it for 4. Yeah, it's within the hardware. So think about it as like the same way that we read the opcode and decide whether this is an add or subtract. You do the same thing for rename. Okay? Questions? Yes. Yeah. Why did it put P6? So the question is about P3. So let's see where it was. So here, right? So at this point, X3 was mapped to P6, right? So now we go to this instruction. So now we go to this instruction. As I said, source register, you don't do the remapping. You use the previous mapping because this is a raw data hazard kind of situation. You need to use the previous values for the sources, okay? That's why you don't introduce a new map. But for the destination, in order to remove the output dependence and anti-dependence, you want to use another registers to reduce the chance of the collision, okay? So that's why I actually introduce a new mapping here. So I say X2 is mapped to P2, X5 is mapped to P5, but then since X3 is the destination register, I introduce a new mapping. So I said that, okay, this was the current mapping, I introduce a new mapping. So I put P8 here, okay? From then on, whenever I see, so here, whenever I see X3, that is P8. Until Px3 is another destination register, and that's when we introduce a new mapping. Okay, so if it's continued to be source, it's going to continue to be P8. Okay, does that make sense? Yeah. Yeah, when we are, so as I said, when do we free? We free the old destination registers when the instruction is retired. So when that instruction is retired, so for example, when this instruction is retired, you free the old destination register. You free P3 basically. Okay. And then what will happen if you don't have free registers? You stall the processor. You wait for the previous ones to finish. But usually it doesn't happen because you usually have significantly more number of physical registers to your destination registers. Someone calling me? Okay. Yeah. Yeah. So when you have like, it's like a scenario like this, right? So X4 and X4, use old mapping for this and the new mapping for this. Yeah. What is the ratio is that like you have for RISC-V you have 32. So typically you have like 128 or even more for physics. But it also depends on the processor. No, the physical ones are the actual real ones. They're actually, you store the actual physical registers in the pipeline. The architectural ones are the fake ones. So you actually have like literally a bigger register file. Uh-huh. So I'm actually, yeah. So this would be how it looks like, right? So you introduce your rat here, okay? So this is like, where you read the instruction and when you decode, you put it into rat. Rat gives you the actual physical register. So now this is P1, P2, could be all the way to P127. And this is when you actually read the physical register file from the register. Okay. So from this point forward, in this particular design, by the way, there are multiple ways of designing this. There is another way of like just propagating tags that I'm going to show you next time. But for now, at this point forward, everything is physical register. So I don't no longer understand what is X1, X2. I only understand P1, P2, P3, and so on. So what it means is that basically these lines are no longer 5 bits. It would be log of whatever size of the register file. So for example, it's 128. I need like 7 bits, 8 bits. Yes. It's usually just the last mapping, right? So it's the final mapping. In the ROB, you also keep track of the old destination mappings, because if you need to recover, you would recover to the previous. Uh-huh. Uh-huh. So you mean like a scenario like this? X3, X3? Yeah, so renaming doesn't solve the raw data hazards, right? So it's still, as you can see, you have P6 here and P6 here. So it means that I still cannot run this before this, okay? Because there is an actual dependency between these two P6s. But what it does fix is the scenario like this. So look at this, guys. Look at this one and this one, right? So as you can see here, you have P6, P2, P1, P8, P5, P2. I can now reorder this and run this before this, right? And you want that to happen, right? Because these two are not dependent to each other. But this, guys, you cannot run it before this because there is an actual dependence. Yeah. It goes to the free pool, yes. When you are freeing things, you put them back into the free pool. Yes. Okay, so basically in this initial example, if I go back here, so what you free here, okay, so whenever this instruction retires, what you free is P3, not P6. You free P3 because P6 is still needed for the future instructions, but P3 is no longer needed. Where do you store P3? As I said, you usually store P3 in ROB. You don't store it in the RAT. In the RAT, you always just maintain the latest mapping, but you always store, for each instruction, you store the old mapping into the ROB. Okay? Yeah, this is also the example there. This is the new one. This is you add the ROB here as well. And as you can see now, the rat also written to the ROB and back and forth. And this is what we have so far, okay? So I have a mechanism for recovery. I now also have a mechanism for removing data hazards by using I have a mechanism for removing the new data hazards. I still haven't talked about how do we fix the memory hazards, but for now, don't worry about that. But I'm going to still have the raw hazards, and you need a mechanism for tracking things, okay? So just keep that in mind. That would be it for today. Yes, yeah. That will be it for today. Next time, we're gonna actually talk about the first one. How do we do the scheduling? How do we execute these things, and so on and so on. All right? Yeah.